hear me well? From here? Yeah? Okay, good. Good morning, everyone. Thank you for the invitation and for allowing me to talk about what is my passion, which is the evaluation of AI systems. I'm going to start with what was my passion many years ago. I remember as a teenager, one of these summers, that we didn't have internet or mobile phones or anything like that. And I remember spending the whole summer playing with my ZX Spectrum, trying to make it think. And of course, it only had 48K, not parameters, bytes. So that was, you could even count them and see them, all of them, during that long summer. I think I reinvented three-value logic during the summer. I thought that being able to say, I don't know, that was a key issue of thinking. Actually, this problem of AI systems not being able to say, I don't know, has come back recently in some of the research that we have done in our team. But today, I'm going to talk about what a different thing that, in a way, changed over the years. I gave up to the idea of building AI systems, and instead of that, I left that responsibility to some other people, and I thought, okay, maybe what we have to do is to evaluate AI systems, and I've been doing that for a long time, which in a way you can say, okay, maybe that's because you don't have the capability of building them, but everybody is doing the same these days, because unfortunately, we have relegated that time. Okay, here we are. So I was saying that AI evaluation is not in good shape. So I'm going to talk about some of these problems and then try to present some kind of an approach that solves some of the issues, especially in the context of people claiming that we need a science of AI evaluation. So the first question is the general question, why do we need AI evaluation? Many reasons. But one reason is that we want to know what AI can do at different times of progress and when we apply this question to different AI systems. So there's this typical question about whether they can make a cup of tea or coffee. The answer is no, especially you have an AI robot just coming into a random house and trying to find the ingredients and the coffee machine and making it work. So the answer is no for that, but we can give very good answers to some other questions. We can say, okay, are we good at recognizing human faces? And the answer is, of course, we solved that problem many years ago. Well, I wouldn't be that sure that this is that solved as some people claim, especially if you just look at some of the groups inside the population, how well these models work for some specific groups. And some people are even claiming that these systems, they might have developed or may have developed or have a theory of mind. And I know Michael, he presented this paper 2 years ago. Archive is very good because you can see the story of a paper. So the title was Theory of Mind May Have Emerged. Then he had to retract a little bit and say, okay, might have spontaneously emerged in large language models. And then the final title of the paper is much more mundane. It is just evaluating large language models in theory of mind tasks. So, well, something that perhaps you get a little bit, you get the illusion of theory of mind, then when you look into it, or you get a lot of criticism, then things are a little bit different. Of course, people are saying that some of these systems, I'm talking about 2023, not even today, they may have become conscious. I like this one, because The main reason for this guy to say that these systems are conscious is because this person is a Christian. So we are fine. We are fine, because I'm not, so okay, I'm fine. I don't think that, so I think it's in the eye of the beholder, this kind of being conscious or not. Of course, they can create deadly chemicals. Some people are saying they can. How dangerous this is, I think it is pretty dangerous, and it is becoming more so. But yeah, there's a lot of discussion and disagreement on whether we are at a very high risk now or the risk is still low. There's a lot of discussion about this, not only in chemistry, all this CBRN, so chemistry, biological, nuclear, and of course cyber. All of these questions are critical questions for which we need answers, especially for AI safety. And then, of course, the typical question, back to Turing. Can they think? And this question comes back again and again and again. Every 2 weeks you see a paper about whether they can think or not. And the most famous one this year has been one paper from Apple, The Illusion of Thinking. And actually, I think that the results show the models are doing quite well, not in thinking, but they're quite general. So they make basically, I think my interpretation of the results is completely different from the interpretation of the results that they do. So this is also something that happens. You do the same experiment, and people interpret the results in different ways. So yeah, there's also a paper on arXiv just appearing just a few days later, written by C. Opus and A. Lawson. This is the illusion of thinking. And it is not difficult to guess that the first author is Claude Opus. So it's a language model. So of course this is a joke. This has been corrected with the new version on arXiv. But yeah, some of the criticism in this paper, criticizing the previous paper, they were constructed or written using a language model, okay, which is something that a lot of people are doing these days. So all of these questions, we disagree strongly on the answers, so that I'm not saying people in the street, I'm saying scientists, people who are in these areas, they basically disagree on what AI systems can do. So we don't really have a good agreement in AI evaluation. So let's try to fix it. Okay, so what are the main problems? First, it doesn't have any explanatory power. Okay, we say, okay, they think, are these the words that really explain what they can do and what they can't do? Are we talking about capabilities? Are we talking about propensities? What kind of language are we using? Are we still using words such as thinking? Is that consciousness? Are these the words that we should use in AI evaluation? And no predictive power. You say, okay, this system, can I predict out of the box whether this system is going to perform well on a new task? I don't really know. We don't have models about that. We don't have predictive models about the behavior of AI systems. Well, there are few, but this is not the typical way you see AI evaluation papers going around. Mostly because benchmarks, they don't measure what they say they measure. They measure a lot of things. You put a lot of things, even you have a benchmark about maths, and you put a lot of things inside that benchmark, and they measure linguistic capabilities as well, and reasoning, not only maths. Of course, math has to do with reasoning, and math has to do with language, but there are many other things that you include in these benchmarks, so everything is confounded. Then you have levels. You have this percentage. You have 70% on this benchmark, and then you have another language model or another AI system, you have 80%. It's okay, fantastic, this is better than the other. Well, it depends on the examples it succeeds on. Yeah, that you can really tell that one system is better than the other. But the worst thing is not that you can use these numbers to compare two systems. The worst thing is you cannot compare 70% on a benchmark with the 70% of another benchmark. And we are changing benchmarks every year. So when we are saying that we are getting 80% in a benchmark, what does it tell, especially the public, about the progress in AI? Not much. They saturate. Once they get to 95%, the rest, the 5%, is either too difficult or it's noisy. So maybe you have some mistakes in the labeling of the examples, or they are not easy to grade. There are many reasons why you cannot get beyond maybe 95% or 97%. And what you do is either you fix the benchmark, adding more complex instances, you deviate from the original distributions, you are measuring a completely different thing, or you just throw it away and you create a new benchmark. And you call it pro or something like that, or hard, and you create a new benchmark. And you have MMLU pro, you have MMLU hard, you have MMLU super hard, and that's what we are doing. So these saturate, and we basically replace them with new ones. And even when we try to analyze the dimensions of performance, we can use factor analysis on a population of AI systems in the same way we have been using factor analysis on a population of humans. We can do that. We can create some factors. But whenever the paradigm changes from the traditional LLMs to the chain of thought of reasoning LLMs, then all of these factors change. So something that was kind of insightful for some population of AI systems is no longer insightful for a new population of systems. It's like you do factor analysis on a human population, and you go to chimpanzees or the other way around and see, and you expect that the same dimensions they're going to hold. This is not the case. Well, okay, let's build the science of evaluation. Everybody's talking about this. That was Apollo, a third-party evaluator, and they wrote, we need a science of evals. Okay, they call them evals because it's cool. You call them evaluations, you are old and boring. So yeah, we wrote a response. This is me and Nando. I don't know if he's in the audience. He's part of our team as well. So there was a response. There are many things there. I think the oldest citation was 2022. So you want to build the science of evaluation and you ignore everything that had been going on, not only in AI, but in other areas such as psychology or comparative cognition for decades or even centuries. That's really impressive. If you want to start a science of evaluations, ignoring hundreds of years of knowledge, then yeah, you're destined to failure. Okay, so yeah, this is one of the big names at the AIAC, Jarin Gal. He's a great researcher. Also, he's emphasizing that we need a science of evaluations. This happened in a few months. And even recently, you have this institute. It is no longer called the Safety Institute. It's called the Security Institute now. Now, they also have a team, a great team, by the way. I'm not saying that this is not a good goal, but you need to do it well, this kind of a science of evaluation. So, yeah, I agree. This needs technological and scientific changes, but many things are already out there for us to reuse or to adapt. Okay, so there are different paradigms. Some of these comments, they come mostly from the paradigm of evals. It was a very recent paradigm, but there are many other areas and many other ways in AI and beyond AI to evaluate cognitive systems or intelligent systems. Okay, so one key thing, and not only for science, for any scientific discipline, is that you have predictability. And people are talking about this a lot. So people are saying, can we predict whether a model is going to, or even a model that is in the making, is going to perform well on this benchmark, or they are going to show emergent capabilities or something like that? So people are putting a lot of emphasis on this. And that's this recent paper that benchmark prediction with fewer data is missing the mark. I would say that all benchmark prediction is missing the mark. So because you need to predict at the instance level, if you predict at the distributional level, you are not going to solve the problem of out of distribution, which is the problem where everything fails. So you need to understand at the instance level, each example in a benchmark, why are you failing or why you're succeeding for that particular instance. And if you do that, and then you aggregate, you can predict to new benchmarks, new distributions, especially out of the distribution. So we are claiming that we need this instance level data. So this is a set of papers that we've been arguing that we need this. We need to analyze examples, not just benchmarks. And of course, we see predictability. This is from a recent paper last year where we see, in terms of difficulty of the items, we see that performance drops. So if you can anticipate, you can detect the difficulty of an item, of a question, you can anticipate relatively well in different domains whether the model is going to succeed or fail. Of course, you're not going to have a perfect answer for this. Nobody's going to have a perfect model predicting whether an AI model is going to succeed or not for any question. But you can have quite a good predictability, and then you can use that for many things. If you don't have predictability, you can talk about explanatory power, but explanatory power without predictive power, I don't think it's quite reliable. You can have predictive power without explanatory power, but I don't think you can have explanatory power without some kind of a minimal predictive power. So people are rediscovering this. So this is a famous Meta paper where they show that in terms of the time that the task in software engineering, the time that the task requires in terms of hours, you see this nice sigmoid function that you can fit very nicely, where it goes down. In terms of the difficulty, it goes down, as you have seen in psychometrics and in many other areas for decades. So this is nothing new. Actually, this illusion of thinking paper, they say, oh, LLMs, they don't think because their capability drops as a function of difficulty. Well, what would you expect? Would you expect something to be like that forever? Or what would you expect? Do you expect to solve every possible problem? Do you expect to have a calculator? But even calculators, they have a limit. They have a drop in resolution. And so what do you expect? Is it a rhetorical question? You should be able with infinite time and resources and tokens. Yeah, no. Yeah, what do you expect? Do you expect to be infallible?
Yes, if it knew the algorithm for tower
And if you were infallible, like a computer compiler or computer interpreter, but they are not, like humans. Ask these questions to humans, and you will get the conclusion that humans are not thinking. Do the experiment. Do the experiment. So for the first time, we have systems, they look more like humans, and we're criticizing them because they look like humans. I take some of the points from the paper are quite good, but some other points they are not that good. And saying that this is bad when we have that, no, this is not bad, this is good. If you do this with humans, you see the same plot again and again. Try with any student, give them 6 hours to solve Towers of Hanoi, write in all the steps, in some cases thousands of steps, and then see if they get to the end. They won't. Well, and maybe you give them a lot of treats, maybe some of them they reach the end. I think that the interpretation is what matters in these papers. Of course, we would like them to do this, to be able to use a compiler or to use some other tool to run that, and of course, in some cases, they can do it. So, okay, so these are the questions. So now I'm going to present a paper where we introduce general scales in which we can have explanatory and predictive power in an evaluation. So where do we start? We start with defining capabilities. And of course, we can discuss for hours about the taxonomy that we are using. But this taxonomy is based on things that come from psychology, even animal cognition, and of course, AI. We try to integrate a set of capabilities that are understandable by people, and they could capture a great deal of the predictive power for the response of why these models fail or not, or current AI, or future AI, or even humans fail. Okay, so with this we try to explain what benchmarks really measure, which is something that people say, these benchmark measures math, but are we sure that this measures math or reasoning or maybe metacognition or some other things? and then extract ability profiles that can give us a kind of a description of what each AI system is able to do. Okay, so the first thing is, I don't know how much you can see on the right. I will zoom in some of these dimensions. I think that we don't have time to go through each of the dimensions, but I'll read some of them. So this is attention scan, comprehension and expression, conceptualization, metacognition, mind modeling, quantitative and logical reasoning, spatial reasoning and navigation, then different brands of knowledge. This is hierarchical, so the second column is more specific than the first column. And then two extra dimensions that we call atypicality to cover a little bit for contamination, and volume, which describes the size of the problem, okay? Which is related to some of the previous papers. So what we do is, for each of these dimensions, we build a rubric. And this rubric came as a result of a lot of discussions with many of the co-authors of this paper, some of them coming from psychology, from different areas of cognitive science, and of course from AI as well, about what are different levels of demands of each of these dimensions. For instance, in the domain knowledge of natural science, you have a level 0 where the question doesn't require any knowledge about natural science, and you go to level 1, level 2, level 3, level 4, until level 5 plus, where the demand is quite high. This is a very challenging question. Of course, we can argue whether this is calibrated, this is not calibrated. This is our rule of thumb. So when we are saying level 4, it is about maybe 5 in 10 to the 4th people is able to solve that question. Of course, this calibration is very rule of thumb, but just to get an idea. Okay, so level 5 is quite tricky. Okay, we have a rubric. We can do that manually. But instead of that, we do it using a language model. That's a little bit of a big of a change these days, because some of these things were possible a few years ago, but they are quite inefficient because it's quite difficult to annotate 14,000 or 16,000 examples as we do here by humans. So if you take an instance from any benchmark, like this is OmniMath, you take the rubric, which is basically you analyze the question. You need to give a number between 0 and 5. You give the question and the rubric to GPT-4o, and you get this number for AS, because this is the rubric for AS. Okay, you get a 3. Okay, fine. You do this for all the other dimensions, and you get all of these numbers. Okay, fantastic. You have converted. Is it kind of embedding? Well, it's a kind of embedding in the space of capabilities. So where each of these numbers, they represent the demand of the question in that capability. So this is 0 in mind modeling. You don't need mind modeling to solve this question. But maybe you have 3 or reasoning, or you have some other levels that you require for solving this question. Okay, you can do this for many examples. And then what you get, taken from different benchmarks, that's the point of making these capabilities general, that you can take examples from any benchmark or examples from the real world and put all of them together in the same space of demands. So you basically have normalized what are really requiring any system to find the solution for them, either humans or AI systems. Okay? So we have this commensurate space. So what can we do with this? So now we take many benchmarks. We did just a kind of a collection of benchmarks that we found in 2024 venues, AI venues, 20 benchmarks, 63 tasks. And we collected a sample from each of them, a random sample from each of them. And we collected about 16,000 instances, okay? And we annotate all of them. So what's the interesting thing to look when we annotate all of them? Oh, did people do a lot of reasoning benchmarks last year? Or maybe not much about metacognition? Are the levels high? Are the levels low? We can analyze all of that. We are going to see that in a moment. But the interesting thing is, Do you see a lot of benchmarks or a lot of instances in these benchmarks where one thing is high and the other thing is high? You have a lot of reasoning, but you have a lot of metacognition at the same time in the questions, okay? So that's something that we can look, and indeed we can look at that, at the correlations. But I think the most interesting thing is to see, do you find a question where metacognition is high and reasoning is low? Do you find a question where reasoning is high and metacognition is low? The demands. And you can find them. So if you can find them, it's because these two things are different. Are they correlated in humans? Maybe. Are they correlated in LLMs? Maybe. But are they two different things that we should consider a priori as different things? They are. Okay? So in the end, we use 18 dimensions. These are generals. We could have ended up with maybe 100 dimensions. And of course, the correlations, everything would have been very correlated. But we are not doing just bottom-up. We are doing top-down, and we say, OK, we define the dimensions, and then we are going to see what we find, rather than just taking a population of LLMs and see what we find, because this population is going to change every year. So what we find for the examples is something like this. Of course, many things correlate positively, but some things correlate negatively. For instance, the social sciences and the formal sciences, they are typically negatively correlated. So examples that they are heavily loaded on formal sciences, they don't have any demand on the social sciences. That's quite expectable because you look at the benchmarks, either the benchmark is about one thing or the other, but you don't have a mixture. It's maybe MMLU, when you have a mixture, but not mixture in the questions. You have mixture in the benchmark, but the questions are either one thing or the other, so they're typically negatively correlated. So we can see a lot of things here, but the interesting thing is not that you see the correlations. For instance, these are subcategories of metacognition, so they're highly correlated. When it's very difficult, but not impossible, that's the point, to think of a metacognition question where you need to have very good confidence about your answer, and you need to find the elements that you need to solve the question, which is also a metacognition part of the problem. But you can find some examples. Actually, here's an example where you can find two dimensions that are highly correlated with these two dimensions in the questions, but you can find examples where these two things are high and this thing is low. So are there questions that perhaps they have a high value on this and a low value of that? Yes, they are. Even if we just took a random selection of benchmarks from 2024. If we do this on purpose, we do it well, we can get more pure instances, trying to just be loaded on a few dimensions, okay? So now the question, okay, you were talking about annotating this with GPT-4o. How good is it? Or how good is it related to humans? Well, humans are not perfect. So the interesting thing here to evaluate, we took a group of humans, 5 humans, and we annotated a sample of this battery with the rubrics, and then we tried to show the inter-rater agreement between the 5 humans, quite high. So they are understanding the same thing. So typically when they put a 4, they typically agree, maybe it's a 5, maybe it's a 3, but it is quite strange, quite rare that you find level 5 given by one person to this question and level 0 given by another person. So in a way, that means that the rubrics are good or bad, but basically people are understanding the same thing from these rubrics. And if we want explanatory power, it is very important that people understand the same thing. Then the second question is, if we see that people understand the same thing, does an annotator, an LLM annotator, understand the same thing? In this case, GPT-4o. And the answer, after doing Delphi on these 5 humans for agreement, when we take the agreement of these 5 humans and we compare with the label given by GPT-4, the results are quite good in terms of inter-rater agreement. So, of course, there are mistakes. Well, you could call it these mistakes. I would call it disagreements in terms of this on these annotations. So this doesn't mean the annotations are good or bad. It's basically that all of these subjects, humans and GPT-4o, they're understanding more or less the same from the rubrics, at least in the levels, or they're annotating more or less the same. So when you see the rubric, you see some of the examples, okay, You're telling me this is level 3, I understand what you mean. You're telling me this is level 0, you can go to the rubrics, they are in natural language, you can understand, okay? So it gives you some explanatory power, okay? Explanatory power about what? Okay, let's go for that question, and then the predictive power. So this is explanatory power that they give. These are the 20 benchmarks that we included in the battery. And they are 20 benchmarks, as I said before, taken from papers published in 2024 in AI conferences or major AI conferences. And what we see is, I think it's a little bit blurry, so I need to see the details here. So if you look at, this is about math, and this is also about math. If you see the patterns, they're quite similar. So what we're showing here is for each of the 18 dimensions, 18 capabilities, we are showing a histogram. So we are showing how many examples in that benchmark are all level 0, level 1, level 2, level 3, level 4, level 5. For this dimension, most of them are all level 3 and level 4. That's what we see. So with these plots, radial plots or radial histograms, that's what we should call them, we can see whether some benchmarks are really not measuring this at all. Everything is 0 for these dimensions. But they are measuring maybe level 3, level 4. So in terms of how well or how good they are for discrimination in some areas, we can see the answer. We can see the answer in terms of specificity and sensitivity. Okay? So do they measure strictly what they claim they measure? You don't see many pure benchmarks. That's expected. So you don't see a benchmark with only one dimension and everything else is 0, because it's very difficult to have such a pure benchmark, and many of these benchmarks are not that pure. But for instance, you could take addition. Addition will be quite just a benchmark with just additions. It will be quite pure on reasoning and maybe a little bit of numerical reasoning, and that's maybe the interpretation of the question and nothing more. Okay, some of them are very general, whereas this is quite general. I was looking for MMLU Pro. This is quite general as well. There's a little bit of everything. And do we have a lot of instances of level 5? Not really. So they are not really challenging in many ways. Do we have, in some cases, sufficient elements of all the range? Sometimes we don't. So individually, some of these benchmarks, they are very difficult. They are not very useful to discriminate between, especially for very low capabilities or very high capabilities. They are only sensitive at kind of a medium difficulties. That's what we see. Okay? What if we put all of these benchmarks together? We get this. So this is the battery that we present. We call this battery Adele. Annotating demand levels, and then we see that more or less we can cover the whole space. By collecting from different benchmarks, we can have examples on almost every area. And we didn't collect these instances with a kind of a selective bias to fill the gaps. We basically just surveyed the papers in 2024. So, of course, there are some gaps here, and of course, there are gaps at level 5, so there's still the challenge of creating more difficult questions. Maybe these are devised for LLMs that are still not that good, so that's why you don't find, so that's why they are going to saturate very soon if the models they get better. So that's what we see here. There's a room for improvement, but the interesting thing is not that we put everything into a battery, and now we have lost the vision about what they're measuring. Now we can extract any subset of questions and know exactly what they measure. And we can extract some subsets that are loaded on some of these dimensions more than others, and then trying to analyze some of these dimensions separately. We will go to that in a moment. Okay, so how can we do this? And this is the most tricky part. So you have difficult questions. This is a good point of attack, because, yeah, we saw the sum in the examples. Some of these dimensions are correlated. So sometimes it's difficult to find an example where this dimension is high and this dimension is low. So what we do is we take all the examples, the 16,000 examples, and we just plot for one dimension. This is knowledge on natural sciences. We just plot those examples for which the level for natural science is n, and the levels for all the other dimensions are n or lower than n. Okay? So in a way, we're saying, okay, this example cannot be dominated by any other dimension. So if we are looking at this dimension, we need to just to put some conditions that we are really looking at the behavior of this model according to this dimension. We could change, and we played a little bit with this, with this rule about how strict you are in terms of looking for examples that are not dominated by some other dimensions, but in a way allows us to look at these dimensions with some kind of separation. Not perfect separation, of course, we've seen that. It is quite difficult sometimes to find one example that is only loaded on one dimension and not loaded on any of the others. But we can do these plots, and these plots are nice because you can feed them with a logistic curve, and because it's a ratio scale in measurement, it starts with 0, no demand. So you know what the ratio scale is, like temperature, like Kelvin degrees. There's a ratio scale. You have a 0, you have an absolute 0, and you can do additions, and they're meaningful. It's because this is also... so when you do this, you start with this value here. You have the point of 50% probability of success, the point of maximum slope of the curve, and the area under the curve. They represent the same number, okay? We call that number the ability. Okay, the ability of that model, this model is Llama 3.1, on that dimension. Okay, so that's the way we extract the abilities of the system. So we do this for the 18 dimensions for each model. And so here is 4.3. If you're wondering what number this is, it's 4.3. The area is 4.3. This point is 4.3. This is what you find. Okay, so when we say that Llama is 4.3 on natural knowledge, we are not saying that the model is solving all the problems below 4.3. What we are saying is that the probability of success is 50% when the level is 4.3. Okay, this is a typical misunderstanding, especially for people who are not familiar with psychometrics or IRT, where this is quite common. Okay, so we do that for all the models that we explore here. Yeah, you have some of the names there. I don't think you can reach, but some of the typical families, GPT families, and things like that, as when this was done, was the beginning of this year. And you find the sun curves are steeper than others. This come back to the original slides about the performance going down as the difficulty goes up. Of course, that's what we find. Some cases, the curves are flatter. What does it mean? Maybe because the results are better, and then you don't see a point where these the results go down so quickly. But when you have a high slope, that means that around those levels, for this family of models, that dimension is quite discriminating. Okay, it is quite useful to predict success for those models. Okay, so this is ugly. For me, this is beautiful, but you need a lot of time just to look into these plots. Can we summarize for each model, which is one color here, taking the area, can we summarize the capability profiles? That's what we do here. So here you have the Llama family with different number of parameters. Then you have some OpenAI models in red. And then you have some distilled DeepSeek, distilled on Quen. DeepSeek R1 is distilled on the Quen models. And we see different profiles. So they are roundish. First, because they are all large language models, and we know that for the first time in AI we have some kind of generality. So it's quite unusual to find a model that is very good at something and very, very bad at something else. but we find these things. But if we go a little bit general, we find that. Another reason why these are roundish is because this kind of interference where we try to extract one dimension out of the other dimensions, because the equations, they are not completely pure. So it is, even if we do this trick with a curve, still you have some kind of an interference between the dimensions. But still they are not completely round. That's the interesting thing. And they cross, and that's more interesting even. Some of them, they cross. If you don't change the architecture, you just modify the number of parameters, what you get is an onion picture. Each of these models basically is better than the previous model in all dimensions. Okay? That's quite expected. The interesting thing here is that when you mix maybe reasoning models with non-reasoning models, that some of these shapes, they cross. Some of these models, they get better at reasoning, as expected. Maybe mind modeling, quite surprisingly in a way. And for the still models, they get worse at knowledge because they're smaller. They cannot memorize everything, so they have forgotten a lot of knowledge. So they are worse at knowledge, but they're still good at reasoning. So you can find different profiles that explain a little bit the strength and the weakness of each of these models. How can you use this? And I'm going to stop very, very soon for questions. How can you use this? You can just compare a profile with a benchmark or even with a question. You have a single question, you have a question here, you can say, okay, it's inside this. You can even calculate with these curves a little bit, just trying to predict the probability of success with these curves. So just by inspection, you can see a lot of things. You can anticipate whether this model is going to work well for this kind of domain in the workplace, or it's going to work well in this other domain. You need just to calculate that, which is quite fast, just a matter of minutes on any benchmark that you give me, and then you can compare this model with that. And I can say, okay, it's going to go well, it's not going to go well. Okay, that's inspection. Can we do better than inspection? Of course, we know machine learning, but actually, this is one of the easiest problems that you can do in machine learning. It's just a tabular data set with 18 columns. It's just that. Can we do that? Can we do well? Well, we can. We can get predictive power. So this is just, I think this is a random forest. You remember what random forest is? Some of you, okay, still used. With these 18 dimensions, it's just a split on the data, cross-validation, and this is a refinement measure, the error and the error curve, and this is a calibration measure. And when we look in distribution, we see that we get high or decent AUC. These are the level of instance. Take one instance out of the same distribution and try to predict with this random forest whether the model is going to succeed or not. This is, for instance, a GPT-4o. This is some of the O models, maybe some of the llama families. You get more predictability the better the models are, which is interesting as well. In terms of AUC, which is a little bit independent of how good they are. And in calibration, you get good calibration. What are the baselines? The baseline is a predictor based on embeddings on the questions. We had to try that. It is worse. And the other is just a language model trying to predict whether another language model is going to succeed. Yeah, we've been using that for quite a long time. And it is better, a little bit better, at least in terms of IRC. Okay, nice, yeah. You can overfit. You can overfit to the data if you are in distribution. The interesting thing is when you go out of distribution. When you go out of distribution, we train these meta models on some benchmarks and then some tasks, and then we evaluate them on new tasks. Okay? That's a drop in all of these values, but the drop is much worse on these two approaches, and this the method based on the capabilities is more robust to this out of distribution evaluation. Even if we go to benchmark out of distribution, the whole benchmark, you haven't seen a question of that benchmark before. We are talking about the meta models. We are not talking about the models behind that. Okay? We are talking about two levels here. We're talking about the predictor of success of any of these models. we get that, of course, this goes down, but still resists, and the other models, they perform quite poorly. Why? Because they overfitted. Because we are using general capabilities, our tendency to overfit is lower. Okay? So, yeah, I'm going to just close here so that we can have maybe at least 1 or 2 questions, sorry. Yeah, but the summary is that we can do these things, we can have the levels, we can extract a profile from benchmarks, we can extract a profile from AI models. You have the code, everything here if you're interested. It's quite easy to apply. Just annotating 16,000, you can use these annotations already, but you can annotate your benchmarks if you like. This is quite fast. And yeah, that's something, if you want to use it, please use it and report. And yeah, thank you.
Any questions?
Not really a question. This is really beautiful work. And I think one of the things people should notice is it's not comparing against human performance. It's defining performance using the dimensions that we understand from human performance, but then measuring them in some sense, just absolutely in terms of probability of success, right? So I think that's such a big advance over what we have right now. Maybe a question is, so I'm a practitioner, I'm trying to apply LLMs to some problem. What's your advice for how I should evaluate different possible LLMs or evaluate the system that I build out of those LLMs?
Yeah, my suggestion would be take representative examples from the distribution that you want to apply your model to. So it's like creating a kind of a benchmark. You go to a company, you want to apply this for these kind of problems, okay? Customer service, give me maybe 100 examples of the things that you want to solve, and then you annotate them with this. You can also keep some of them as for testing how good, and then you annotate them, you build a model of predictability, you get these plots, and you see if the plot basically subsume or not your distribution. You can even analyze what kind of examples they have higher demands that your models are not going to be. Maybe you can detect these are going to go for humans. You can do all of this. And note that we don't need anything else. You just give me the examples because they are general properties. We apply the rubric. We just need just an off-the-shelf LLM to do that for you. And in a matter of seconds, you're going to have all your examples being annotated. And even you can build a model with a random forest. It is just a matter of seconds or minutes. So that's what I would suggest. Problems. Of course, not everything is fantastic. Problems. Maybe for this problem, you realize that you don't get high predictability because these dimensions are too general for your problem, and maybe the variance that you observe in the performance of your models is not explained or not predicted by these dimensions. Then my suggestion is, okay, this is a methodology. You can adapt that methodology. You can even create some kind of a specific dimensions for your domain that maybe they are useful to give you more predictability. But I think that this is not the first time IRT in psychometrics, some other areas, they're basically saying evaluation should be evaluated. So evaluated should construct a model that we would need to go to somewhere and say, okay, is your evaluation doing right? So with this, you can do that. That's the second step, that we are building a model and see how well these dimensions are predictive or not. If they are not predictive, you can remove them. That's fine. But you can do all of that a posteriori because a priori, and that was related to your first comment, we didn't take the dimensions that we think they are good for LLMs or good for humans because we don't know a priori. Maybe there's a new revolution in an algorithmic improvement this year on large language models, and then maybe it's a new dimension that people are talking about. Should we include hallucination as a dimension or resistance to hallucination or something like that? Maybe we should. Something that we need to explore because we are in terra incognita. In terms of the capabilities of the systems, we can get some inspiration from humans because we want at least that humans can understand these words. Oh, reasoning, okay, I know a little bit what you're talking about. But yeah, I think that it's going to depend on the problem. And we are going to be adapting more and more to the capabilities that are going to be more predictive and explanatory for AI systems of the future. Thank you.